a couple good questions during the break, so maybe I'll just answer them. Here. So one is why is this P? Got it. So again, we're going to fill n electrons in orbitals. U is a unitary matrix, so it's m by m. Sorry, I'm really writing dagger, apologies. So I should have written it the other way, but okay, let's look at U dagger J A. So the index, yeah, they wrote this weird.
You turn your microphone.
Do I turn it on or off?
Yeah, just keep it on.
Okay, there's just a typo. It's actually the ordering I've been using is either. Okay, so U is an m by m unitary matrix. The columns, which run over the orbitals that we're going to fill or unfill, naturally then decompose into the n columns that I'm going to fill and the m minus n columns which are empty. Now, when I form P, I'm contracting U with U star, which corresponds to basically throwing out these columns, just truncate U down into a rectangular matrix, and then forming U dagger U just with that triangular, that rectangular part, right? That's what this means. But because these are contracted together, that's then clearly invariant under any n by n unitary matrix in the occupied space. Likewise, because you just throw out the m minus n occupied ones, P is invariant under any rotation in the unoccupied space. So that's why you can see there's a redundancy between U and P of the UN and U m minus n. Yeah.
Sorry, this might be a silly question, but for our 2-point function, or I mean 4-point function as well, are we working at 0 temperature?
You could do Hartree-Fock at finite temperature. It's kind of interesting. Then your variational thing is not going to be to minimize the energy, but to minimize the free energy. I'm going to do this at 0 temperature. And so because we're doing it at 0 temperature, that's why that 2-point function is a projector. If you did things at finite temperature, then the eigenvalues would be between 0 and 1, corresponding to the, the analog of Fermi occupation. Yeah. Yeah. Another thing I'll just clarify is, as I said, there's many types of IVC. I focused on one Kekulé and figured out what it looks like, because it happens that that type of one opens up a gap. There's other types like the Kekulé Y, which don't open up a gap, but nevertheless, they are possible that there's something that could happen. Okay, so let's now consider the variational problem. Using Wick's theorem, we know that the expected energy, given a particular Slater determinant ansatz, we can just substitute in these values for the expectation of the 2 and 4-point functions together with the general form of the Hamiltonian we wrote down. And so what we're going to get is first the one-body part, 1ij pji, coming from the expectation values of Seidegger psi. And then we get the two-body part. I had this general V I J K L 2. And then I write in this P L I P K J minus P L J P K I. So in this context, the expected energy is then a sum of 3 terms, the non-interacting part. This term here, we call the Hartree part of the energy. And this term here is called either the Fock or the exchange term. So now let's just figure out in this totally general abstracted form, what is the condition on P in order to minimize the expected energy? And that leads to the idea of self-consistent Hartree-Fock. So we can't just take that functional and minimize over all P because, I don't know, you might, for example, just set P is equal to 0. But we know actually two things. One, that P needs to be a projector to be a Slater determinant, and also that the trace of P is just the number of electrons in the system. So really we need to optimize over P subject to these constraints. It turns out this is actually the important one. This one won't matter too much. So to do that, we do the general trick of introducing a Lagrange multiplier. I'll define a kind of Lagrangian L of P is the energy part. And then I'll do minus trace lambda P squared minus P. As I said, I'll skip over it now. It turns out this part of the constraint doesn't matter too much. Only this one matters. So this lambda here is a m by m matrix of Lagrange multipliers, which then enforce the constraint that P squared is equal to P. And then what I need to do to find out what the energy minimum is look for solutions where dLdP is equal to 0. Okay, and then using this expression here, I can then figure out what that is. So this is somewhat tedious, but I get dl d p ji. So if I take the variation with respect to this particular component, it picks out v1 ij. The interacting part is quadratic, so you end up getting two equivalent copies, which cancel the factor of 1/2 there. B, E, 2, A, I, J, B, B, A, minus V2, A, B, J, B, A. And then finally, there's the Lagrange multiplier part. Here I'm going to suppress the indices because it takes a kind of nice form. You get lambda P plus P lambda minus lambda. Okay, so the right way to think about this is dLdP defines a matrix. Part of the matrix is obvious. It's a single particle Hamiltonian. This part of thing defines a matrix in the ij space, but the matrix is actually a linear functional of the P. Okay, so the A, B are summed over here. This combination here, these three terms together, is what we call the Hartree-Fock Hamiltonian. But implicitly, it depends not just on the matrix elements, but the current guess for what the projector is, right? It's a linear function of P. And then you have this Lagrange multiplier part. And apparently, this then gives a matrix element, matrix equation, which needs to be 0. And you need to adjust lambda and P in order to make this thing 0. Now, when I look at this, this is really not very, the meaning of this thing is kind of obscure. But it turns out that there's a way to rewrite this, which then has a very transparent physical interpretation. Over here. So using the fact that on the constrained manifold, P squared is equal to P, you can show that that condition there is satisfied if and only if the Hartree-Fock Hamiltonian for current guess P commutes with P. So I leave that part as an exercise to the reader. And it's not too hard. You just take that equation and you first multiply from the right by P. And you use this interesting fact that when you right multiply by P, this lambda P squared is lambda P, and it cancels that one. And you do vice versa. And when you work it out, you get this cool fact that all this stuff goes away It's kind of interesting. Okay, so another way to think about the Hartree-Fock consistency condition is that the Hartree-Fock Hamiltonian commutes with P. Now this is a nonlinear equation, right? Because this is linear in P and this is linear in P. So this is actually a quadratic equation. Okay, so how do I make, suppose I have a current guess for what H Hartree-Fock is. What do I know about P? Well, if they commute, they're simultaneously diagonalizable. So we know that, suppose I found an eigensystem, sorry, H U is equal to U times diagonal E. So I just diagonalize it, and if I was to unpack this notation here, what I'm finding is a unitary matrix, I alpha, and a spectrum, E alpha, so the eigenbasis of the Hartree-Fock Hamiltonian. In order for these to commute, we know that the projector is diagonal in the alpha basis, and because it's a projector, its eigenvalues are just 0 and 1. So in other words, the projector just corresponds to diagonalizing the Hartree-Fock Hamiltonian, and then either emptying or filling the various orbitals. Okay, so in other words, we know that P is exactly equal to alpha running over some occupied set of Hartree-Fock orbitals times U I alpha U star J alpha. Right? This gives a matrix which clearly commutes with U and whose eigenvalues are either 1 or 0 for the unoccupied, or sorry, occupied versus unoccupied. So this will be the general form is something that satisfies that condition over there, and it's a projector. Okay, so that leads to the following very transparent interpretation of Hartree-Fock as a kind of iterative procedure. Let's see. So what is the self-consistent Hartree-Fock algorithm? Oh, do I need that term anymore? Self-consistent Hartree-Fock. So step 1, pick a guess. Pick some projector just as an initial guess. 2. Then, using your knowledge of the matrix elements, form the Hartree-Fock Hamiltonian, which is just a usual one-body Hamiltonian, right? It's just a matrix in the space of single particle orbitals. Then diagonalize the Hartree-Fock Hamiltonian. E. And then at the next step, you make an updated guess for the projector, which is to fill the lowest energy orbitals of the Hartree-Fock Hamiltonian. So 4, you update P to be equal to for the low E alpha, for the n lowest E alpha. So as you do this, you tend to find that the energy goes down, and eventually you achieve a fixed point where when you do this step 4, you just come back to itself. So you've found a particular projector which projects onto the lowest eigenstates of the Hartree-Fock Hamiltonian for that same projector, and that's self-consistency. So once this iteration between 1 through 4 converges, you found a projector which satisfies that condition up there. And this is the idea of the self-consistent Hartree-Fock iteration. In practice, this doesn't converge particularly quickly, and there's a long literature in chemistry about various improvements like optimal damping approximation and so on. lots of people are using this sort of thing for ABC graphene and magic angle graphene and so on, and it's kind of important if you want a code that works well to actually make use of those more sophisticated ways of doing the optimization. Okay, so that's Hartree-Fock in general. Now what I want to do, and hopefully I'll be able to finish in this lecture, is that was totally abstract. Now what I want to do is take a particular type of Hamiltonian, which is the sort of Hamiltonian that applies to these various flat band systems or continuum models in general, and then show that the structure of Hartree-Fock and the Hartree-Fock functional takes a very kind of cool form, which looks like a nonlinear sigma model in K-space, where the structure is determined by the quantum geometry of the wave functions, like the Berry curvature and the Fubini-Studi metric. Okay. Any questions before I start?
Okay.
So what we now need to do is, in this abstracted form, I just assumed a totally general VIJKL. But let's actually work out what this is in the context of the sort of Hamiltonians used to describe graphene and so on within these continuum approximations. So what's the starting point? We have some single particle band structure, long K, whatever it is. It's a conduction band, a valence band, some other bands. So I'm going to label throughout the bands by some index, n equals 1, 2. And there might be another one copy in one valley and one copy in the other valley. The valley index you can kind of, for now, just group into the band index and just thinking of it as part of the indices of the bands. Now, very importantly, if I'm going to pass from the non-interacting picture to the interacting picture, I need to know not just the energy of the wave functions, E and K, but all importantly, to understand the effect of the Coulomb interactions, I also need to know the wave functions in real space, phi and K. Okay, so let's say maybe you've done DFT or some other approximation, and you've done the sort of single particle treatment, and you have the energies and the wave functions. And now I want to put back in the Coulomb interaction in order to study strong correlations and so on. What's the resulting form of the Hamiltonian we get? Okay, so the sort of model people generally consider, if you're restricting to some low density description of a graphene-like system, is a Hamiltonian where you take the single particle part, usual non-interacting picture, and then I add to it a Coulomb interaction, which just takes a density-density form. And you should have in mind, for example, that the Coulomb R minus R prime is, roughly speaking, like 1 over R minus R prime. The details here technically depend on the experiment. Like a lot of these experiments on 2D materials, there's a nearby gate, and the gate screens the Coulomb interaction. So at long distances, it's not actually 1 over R. It passes over to something dipolar or exponential. But anyway, throughout this discussion, I'm going to leave it generic. Okay, so how does that information show up in the Hamiltonian, right? This is ultimately a large many-body Hamiltonian. It's obvious how the energies show up. The way that the wave functions show up is actually in the form of the density operators, and in a very important way, actually. And this is where the idea of band geometry ends up being really important for the energetics of a system like this. So let's remind ourselves, what is the density operator I'm talking about? Well, n of r is, of course, psi dagger r psi r. I could sum over spin if I want, but I won't for now. I'll just suppress spin. And then I can substitute in that the field operator, psi of r, is a sum over bands and momenta of phi n k r c n k. So when I then go to compute the density, this is something like C dagger M K prime, C N K, phi bar, phi M K of R. So the matrix elements in the single particle basis, where things are specified by band in K, clearly depends on the wave functions. So that's why you need to know the wave functions in order to get an accurate Hamiltonian. This is kind of an interesting theme. For example, in descriptions of twisted TMDs, like Xiaodong was talking about, people often do something, well, they'll do DFT and find some continuum band structure, and then they try and write down a tight binding model, which reproduces the energies of the band structure. And then if it matches the energies, you might assume it's all good and go on to then add interactions in this way. But really, to get the physics right, your tight binding model needs to match not just the energies, but also the wave functions. And we've found examples like in the TMDs, where when you try and make the energies match better, it actually makes the wave functions work. So you need to be careful when you're trying to write down these models to make sure that you have, say, a tight binding model which describes both the energies and the wave functions accurately, because those wave functions show up in the energetics in a very important way through the Coulomb interaction. Okay, so this one does not move. So where does quantum geometry come up? One of the nice ways to analyze a problem like this is in Fourier space. So I can rewrite the Coulomb interaction, H Coulomb, as instead EQ negative Q, where VQ is the Fourier transform of the Coulomb interaction, and N of Q is the Fourier transform of the density operator. This is a rather nice way to write it if you have translation invariant Coulomb interaction, as we do. And now what I want to do is work out the form of the K-space density operator in terms of the wave functions. And this gives rise to a quantity called the form factor. Or maybe you'd call it the vertex. Okay, so what we would then find is that when we substitute in this ansatz here and take the Fourier transform with respect to R, we're going to need the following quantity. D squared R. R. M. And we just define this thing to be lambda M N K Q, where implicitly K prime, now let me make sure I get this correct, is equal to K minus Q. So how do I know this? Well, when we expand these, we know that they, when you integrate over all of space, you know that there must be a lattice momentum difference between K and K prime, which is equal to Q mod G. Right? Because momentum is going to be conserved, and the momentum of this operator is Q. So when you compute this matrix element, there's two ways of thinking about it. You can think of it as depending on K and K prime, but actually K prime is forced to be equal to K minus Q modulo G. The K and K prime live in your little Brillouin zone. Okay? So this matrix element here I can then think of as a function of the two band elements, the momentum of the state you start with, and then the momentum transfer with K prime determined through this. And this thing is called the form factor. Perhaps a nicer notation for it. Maybe a less complicated way of thinking about it is it's just a matrix element. A lot more compact way of thinking about it on the Mn. Okay, Q is just a single particle matrix element between state K minus Qm, the operator e to the negative IQR. Okay, this is just the Brockett way of writing the interval up there. So once we have this, we now know that the density operator N of Q, which shows up in the Coulomb interaction, I just substituted in M K minus Q psi N K lambda M N. I hope you can see that. Okay. So this one body operator has a matrix element which will scatter from band N to M and transfer from momentum state K to K minus Q with an amplitude, which is the lambda. So at this point, it's somewhat tedious. Once we know what N of Q looks like in terms of those form factor, and we know the Hamiltonian just looks like N of Q, N of negative Q, it means that all the information we need to compute the matrix element of the Coulomb force are now encapsulated in these form factors. And the cool thing that we're going to show is that the form factors at small wavelengths are uniquely determined by the quantum geometry. And so if you know the quantum geometry, you know the matrix elements, and therefore they show up in the form of the Hartree-Fock energy. Any questions about that? Yeah.
I mean, yeah, maybe I don't see where this is going, but when you say so if you want to relate this to the quantum geometry, that is when Q is small, right?
Yeah.
Okay. And what does that mean then? And what about large Q in your interaction terms?
Yeah, I mean, basically, it's, you know, if you do it on a computer, you don't make these approximations, you just sum over all Q. But what we'll find is that for the Fock term, the strength of this tends to depend decay as a Gaussian in Q, so that the low Q ends up being more important than the high Q. Yeah. The reason you can see it is as follows, like, consider one of these wave functions. Ultimately, it involves momentum which are near the K point. And so the wave function, by kind of definition, sort of changes slowly. It doesn't have very many high Q components. So if you take two wave functions which both vary slowly and ask what's the matrix element for e to the IQR, if Q involves large momentum transfer, there'll be a small matrix element. So this thing tends to just fall off as Q is large. So it will then be heuristically justified to actually focus on this equation by taking the small Q limit of the lambdas. Yeah. Yeah, I don't think it, VQ also helps because VQ goes like 1 over Q. Well, it depends on the interaction. If you have an unscreened Coulomb, then V of Q is 1 over Q, so the smaller Q is relatively more important. If you have a short distance interaction, then V of Q is more constant. You can't really appeal to the V of Q. I think really more the reason is actually that the lambda themselves just decay as a function of Q. Yeah. Okay, this is extremely tedious and technical, but I guess we have to do it once in our life, or I've done it too many times because I forget it over and over again. But you can see it's perfectly well defined now. You take that version of N of Q, You substitute it in twice, it's going to be a kind of mess of a C dagger, CC with a bunch of indices and the form factors. And then we can evaluate it at its expectation value using Wick's theorem, right? So basically, we've derived what is the form of the Vijkl in terms of a product of these form factors and a sum over Q. I will perhaps spare you the pain of doing all the steps and just say that the expectation value of the Coulomb interaction for that sort of Hamiltonian there then takes the following form. Q. Because the form factor, there's two factors of the density operator, so the form factor is going to show up twice, MP. Once for n of q, and then it's going to show up once for negative q, MP, n, O. And then I'm going to have a Hartree and a Fock type expectation value. So the Hartree one is basically when you take the expectation value of n of q and times it by the expectation value of n negative q. That's one of the possible Wick contractions. And so you can see the orbitals that get contracted as MP with a form factor. This here is just literally n of q. This thing here is n of negative q. And so this term here is just the expectation value, this first part of expectation value of n of q times expectation value of negative n of q. That's the Hartree part, which is written here. The Fock part is not very intuitive. I mean, this is kind of intuitive. It says that the energy is the expected value of the density, and then you just evaluate the Coulomb energy for that particular density profile. So Hartree is kind of obvious. The Fock one involves exchanging the order of these, and so it kind of entangles them in a weird way. C dagger M. Two. It's a product C dagger Q C O K2. If you want to work it out for yourself, it just involves exchanging this one with this one. Okay. This notation is terrible for the moment, but I'm going to simplify it in a bit to make this less painful. Okay, so I think in the interest of time, I won't discuss the Hartree term at all, because it's the Fock one which is most interesting as far as the physics of driving intervalley coherence. So I'm mainly going to describe that Fock term. The Fock is the one that arises only because of the anti-symmetry of electrons. If they were distinguishable particles where you didn't anti-symmetrize, you would just have the Hartree part. Fock part comes from the anti-symmetry. Okay, so let's simplify this and make this disaster go away. So we need to know the expectation value of this projector here. And let's assume for simplicity that the state I'm looking at doesn't break the microscopic lattice translation. So that I know the general form of the projector must conserve lattice momentum. So I have C dagger M, K minus Q, Cn. K prime. Maybe I can just write it like this. If you took a general expectation value like this between 2 points that differ by Q, it's going to be non-zero only if the momentum difference between them is some reciprocal vector. So I'll write that as a condition that Q needs to be equal to a reciprocal vector, where G runs over all the reciprocal vectors. And then it could be totally arbitrary, the NM as a function of K. Okay, so this is the assumption that my expectation values preserve lattice momentum. Okay. And then what I can do is once I make this assumption, I can simplify this expression here. So originally, though I passed over it, this expression has a sum over the momentum transfer and then independently K1 and K2 coming from the sum over K, which is inside the definition of the momentum operator. So to start, I have an independent K1 and K2. But now I know that this is only non-zero when K1 minus Q is equal to K2 modulo a reciprocal vector. So that then implicitly determines K2. So rather than having a sum over K1 and K2 independently, I'm just going to get a single sum over K, and this will simplify. So the result we then get for the Fock type term, I'll write it as E Fock, is -1 over 2V, sum over Q. And then I'll write it out here, P0M. Okay, times finally a lambda. Okay, so all I've done here is I've substituted in that K2 is equal to K1 minus Q, and then replaced K1, just called it K. So the claim is that's this expression here. You'll see the indices work out. And then you sum over all the bands. So you'll notice that it kind of works in a nice way. If I just think of these as matrices, it's a trace of P lambda, and then it's just like a trace over the product of those four matrices. Yeah. Okay, so that was a bit of a disaster, but it turns out that there's this intuitive structure to what sort of projector will tend to make the Fock term as negative as possible. And this is where we're going to derive the nonlinear sigma model sort of description of Hartree-Fock. Okay. So maybe I'll just say this in English. So let me make these indices implicit. So all of these are matrices in the band space. What I have here is a trace over the product of these four matrices. So now we can ask, suppose we know what the projector is, what states are occupied at a particular K point. The Fock term wants this thing to be big. So how would I choose the projector at K minus Q in order to maximize this? So the way to think about it is as follows. Let's pretend for the moment, and I'll correct this in a second, that lambda is actually a unitary matrix. And so this lambda p lambda thing I could think of as contraction by a unitary or conjugation by a unitary matrix. In general, lambda is not unitary, and I'll come to that. But just for the moment, let's get some intuition. So it's like you start out with a projector at K that occupies some particular plane. And then when you conjugate by lambda, it rotates to some other plane. And the way you would maximize this is to then have this projector span the plane defined by the rotated version of P. Or another way to put this, if you looked at lambda p lambda, you can easily show that P is a matrix with eigenvalues of either 0 or 1. Lambda p lambda you can show in general is positive semi-definite and is a matrix with eigenvalues between 0 and 1. And the way you would maximize this is to choose the projector here to have support on the largest eigenvalues of lambda p lambda. So it's kind of like this defines a particular space, and you want the projector here to align with that space. So that's sort of the intuition. So if you think of it as like the projector at this different place at K minus Q should be parallel to the transported version of P of K, where by transport, I mean conjugation by this matrix here. So I'll make this more precise in a second. You could sort of think of it then as being like, we want the projector to vary slowly with respect to this notion of transport, how to compare the projector at two different points in space. And indeed, actually, when lambda is unitary, this will exactly correspond to the usual notion of parallel transport that people talk about when you have connections in a vector bundle. Okay. So now let's make this a bit more precise. And to do it, we're going to take the low Q limit of the form factor, because it turns out it takes a very nice structure in that case. Actually, let me keep this here. So how does the form factor relate to band geometry? Well, let's assume the limit that I'm going to focus on is going to be that Q goes to 0, because we'll soon see that it's dominated by this part of it. So what I'm going to do is in the evaluation of the form factor, I'm going to pass to the block basis. So the actual wave functions are phi n k of r, can be related in terms of the block wave functions as ETI kr square root unit cells times u and k of r. Okay, so these are the eigenfunctions, the block wave functions. We strip off the lattice momentum, and the u are now the periodic part of the wave function. So when we then go to compute the form factor, because k and k prime differ by q, when we strip out this part of the exponential here, it ends up having a really simple form in terms of the u. So what you actually get is that lambda mn kq can actually just be written in terms of the block wave functions as u bar m k minus q of r u n k of r. Okay, so the point is you just substitute this into the definition of the form factor, and then we know that k minus k prime is equal to q. So actually the phase part cancels off, and you're just left between the overlap between the block wave functions. Okay, so the takeaway here is that for q small, actually, the form factors we're talking about are just the overlap between the block wave functions at two different points in momentum space. And that's why the quantum geometry is now going to show up. So if we write in a compact notation, we can say that lambda at kq is just the overlap of block vector u at k minus q overlapped with u of k. And then when q is small, we can assume that u of k plus q is equal to u of k plus q times the gradient u of k. So we'll assume we can do a first order Taylor approximation. Then what you find this gives here is equal to the identity plus q dot m, putting the indices back in, mk, and gradient with respect to k. Okay, where these things are just the block wave vectors. Okay, so that's just to say we take the overlap of the block vectors, and at small q, I can do a Taylor expansion, and you get this term here. It's the lowest order part. Now, this should be familiar, actually. This is exactly the Berry connection. So it tells us that the form factor is equal to 1 plus I, the non-abelian Berry connection, U, AU, MN. And it's convenient actually to re-exponentiate this. If we're just working to first order in Q, I may as well instead write this as an exponential, e to the I Q dot A, compressed notation. Okay. So in other words, to lowest to first order in Q, the form factor is actually a unitary matrix whose generator is the familiar Berry connection for a multi-band system. Okay? So you can now see actually to lowest order in Q, I was mumbling about conjugating by lambdas like transport. To lowest order in Q, it really is. It's actually conjugation by this unitary matrix, which is the non-abelian Berry connection. Okay, but we can do better than that actually in order to justify why we could let Q goes to 0 in the first place. So naturally what we want to do is look at second order in Q. And it turns out that to second order in Q, one finds a definition for the form factor which is exactly identical to what people call the quantum metric. So I won't derive this, but you can show from the definition of the quantum metric that this form factor and k plus Q over 2. If I write this as an exponential of a matrix, is exactly IQ dot the non-abelian Berry connection minus 1 over Q, a quadratic form, GQ. Okay, so let me unpack this notation a minute, plus order Q cubed. This here is a matrix in the space of bands M and N. A and G are both matrices in that band space. And if I just define up to order k cubed that this, when doing the Taylor expansion, is the exponential of these two terms, that's a totally generic ansatz, you'll find that the resulting second order part here is the quantum metric. So it's a kind of neat thing. You'll find that G is a real symmetric matrix, which is positive semi-definite, so can play the role of a metric. So I'll leave that as an exercise. If you want to do it, what you can do is you Taylor expand the exponential up to second order. The second order term will have this, but then also the QA squared. And then when you substitute in the definition of A coming from the first order there, you'll find that this corresponds to the usual definition of this quantum metrics or Fubini-Studi metric. Okay. Okay, so because G is, you can show it's a positive definite matrix, it means that indeed, at least for small q, these form factors tend to fall off as a Gaussian. And therefore, because these form factors show up in the expression for the exchange energy, you'll tend to get larger results from the low Q limit. In principle, you could cook up very perverse wave functions where it starts out going decaying as a Gaussian and then becomes large again later, but it doesn't tend to show up if you look at realistic band structures. Okay, so to lowest order, the form factor is given entirely in terms of the band topology in quantum geometry. Any questions about that? Yeah.
I mean, when we think about like moiré systems, can we make some statements what that does to, for example, the Berry connection in terms of absolute numbers? Is it much like larger or something? Because, effectively we're looking at much smaller Brillouin zones.
Well, yeah, I mean, I guess Berry curvature has weird units because it's like units of meters squared, I guess. I mean, it depends whether you measure the Berry curvature as like.
Well, I mean, let's say it's the flux through like a fraction of the Brillouin zone, and then this would be a much smaller plaquette than the moiré basis, right?
Yeah, that's correct. I mean, if we say that in general we know the integral of partial A d squared k over the Brillouin zone is equal to 2 pi times the integer. And in a moiré system, the Brillouin zone is really tiny. So if there is going to be net Berry curvature, it must be that that curl of A is quite large because you're integrating over a small Brillouin zone. Yeah. Yeah, I don't often think about the absolute units of the Berry curvature, but it's certainly a relevant thing to say. If you know all the physics is within a particular K-space patch, what's the total, Berry curvature within that patch? Yeah.
It might matter, right? Because it has some non-quantized things that relates to maybe.
I would need to think about that. Like what the units, yeah, I need to think about that. I mean, you tend to find that in something like a moiré system, the G here is of order the lattice constant, say the moiré lattice constant. And so it falls off over about the order of a Brillouin zone. Yeah. Okay. So now let's go back to the expression for the exchange energy. And we can use the following kind of interesting trick. So it will be a little bit prettier if I take this expression here and make it a little bit more symmetric by shifting k by a factor of q over 2 to rewrite this as k plus q over 2 and this is k minus q over 2 just by a change of indices. And then what I can do is take that expression there and insert in for lambda this expression for the form factor. And to make this a little bit more transparent, let me rewrite this thing here. I'll continue the equality here as e to the I q over 2a. I'm going to sort of Suzuki Trotter it because to this order, to order q cubed, it will be accurate to Suzuki Trotter it. E to the 1/2 q g q e to the I q over 2a plus order q cubed. And then what I can do is just substitute that into the expression there. And you find that the Fock term is equal to a sum a q. Okay, this is a little bit tedious, but I have trace projector at k minus q over 2. Then I write down this thing here, e to the I q over 2a, e to the negative 1/2 qgq, e to the psi q2a. Okay, that was p and then one factor of lambda, and then I write p at the other point, k plus q over 2. And then I get the form factor at that other point. You find that this is equal to negative q over 2. Okay, so that's the general structure of p lambda, and these are all exponentials and traces in the space of band index. So I've rewritten it this way for the following reason. You can see that if you look at this combination here, it exactly corresponds to taking the projector and conjugating by a unitary, which is transport by the non-abelian Berry connection. And likewise, same for this term here. So now what I'm going to do is, because I know I can kind of take q to be small because it's dying off as this Gaussian here, I can take these expressions and evaluate them to lowest order in q. And that's exactly going to give the usual expression as transport with respect to a connection. So if you expand this thing to leading order in q, the q is going to show up in two ways. It's going to show up once from the fact that I'm at k plus q over 2. So I'm going to write the derivative of this, and the q is going to show up once from the fact that I'm conjugating by this term here. So this expression here of is approximately equal to p of k plus q over 2 times the gradient of p, but then plus I q over 2, the commutator of A with P. And you guys will recognize this is actually the general definition of a covariant derivative with respect to a connection A. So if I define D is equal to nabla plus I commutator of A, then the expression is just P plus Q over 2 d mu of P. Okay, so I then substitute that in. And we find that the Fock energy Q of a trace of P minus Q over 2 dP e to the negative 1/2 Q GQ, and then a P plus Q over 2, the covariant derivative of P. Okay, so in general, this is a little bit complicated, but let me make one further approximation. Hopefully you guys will forgive me, which is, let me assume that the quantum metric G, just for simplicity here, is actually a diagonal. Now that's going to be very convenient because if this is diagonal, it commutes with these things, and I'll be able to just, no, actually not just diagonal. Let me assume that GMN of K is actually just proportional to the identity in the band space. Just for simplicity, it's not just diagonal. Let's just assume it's the identity and keep track only of its magnitude to simplify things. Though there are cases where the change in G with respect to the fact that it's not the identity is also interesting. Let me just make this approximation. So that's quite nice because if I assume that the metric as the identity, I can just treat this as a number in the band space rather than a matrix and entirely bring it outside the trace. And then under that approximation, 2V KQ, it just kind of effectively weights the Coulomb interaction VQ with a factor of e to the negative Q GQ, which is the Gaussian damping, which justifies this whole approach. And then I'm left only with the trace of P minus Q over 2 dP, P minus plus Q over 2 dP. And then you can expand this out. You're going to get 4 terms, a PP term, the cross terms, and then the dP squared terms. P squared by definition is P because it's a projector. And you'll notice that the cross terms between P and dP cancel each other by the cyclicity of the trace. And so the net takeaway then is that the Fock energy takes this really cool form, 2V, sum of KQ, VQ, QGQ, times trace of P, which is exactly just the local filling factor. It says how many electrons you've occupied at that point in K space, minus d mu p d nu p trace with this thing contracted with q nu over 4. Okay. So we're approaching finally something that's going to have a nice intuitive explanation. You'll notice that we can now just do the integral over q because this part only depends on k, not q. And so we can do this interval over q here. And if I ignore VQ, for example, that gives something very simple. This is a Gaussian integral, and you're calculating the moment of a Gaussian integral. So the expectation after doing this integral of q mu q nu is actually just the inverse of g. So let me define this metric with upper indices. G upper index mu nu of k, I will just define to be 1 over v integral of q dq e to the negative q g q q u q nu over 4. And roughly speaking, as I said, if I ignore the VQ here, this thing is basically the inverse of the quantum metric. That's why by an abusive notation, I'll think of it as just having upper indices as if it's the inverse of the metric. Okay, so it then takes a kind of cool form. You'll notice that the first part of the Fock energy doesn't depend on the direction of the projector at all. It only depends on the filling. So if you're thinking about like, oh, how does Hartree-Fock like to point in the projector space? What orbitals does it like to occupy? This part's just a constant. All that matters in terms of the direction is actually this part here. So if I evaluate the first part, let me call that E minimum. And then the second part is like an elastic energy, which just adds to it. For K, G, U nu, K. Okay. So this is, I think, a very cool result. If you have rotational symmetry, the G mu nu is generally going to be diagonal in position space, and this then just looks like a covariant Laplacian. Okay, so what it says is that when you evaluate the Fock energy, there's the best you can do, the minimum part, and then depending on how P changes in momentum space, there's like this elastic energy which takes the energy upwards. And so when you ask what sort of symmetry breaking does the system like to do, it likes to pick a variation of the projector so as to minimize this elastic energy. And that's the sense in which I'm saying it's like a nonlinear sigma model, but with this interesting aspect that you should use the gauge covariant derivative of the band structure. Okay, so if there's one kind of takeaway, it's going to be this result. And it turns out just thinking about it this way lets us drive a lot of intuition for when there should be intervalley coherence versus not. How much more time do I have? Okay. Yeah.
That quantum metric is identity.
Yeah.
But if I don't assume that, do I get again same answer?
Yeah, I don't, maybe someone does. I don't have too much intuition for it. I mean, it basically says that rather than just having a number out here in the band space, there's two factors that go inside here that aren't in general diagonal. Maybe I don't happen to know. I'm not sure if someone has worked out an intuition for what happens in that case.
For a chiral two-band system, for example, right?
Yeah, there's lots of cases like in magic angle graphene where there's enough symmetry that this is actually true, that the G is in common between the different bands, and then you can take it out. Yeah. Okay, so I don't know, like 5 more minutes? Is that... this was all very complicated in general. Now what I want to do is to apply this to the particular case of evaluating the Hartree-Fock energy for intervalley coherence. So now let's simplify everything. Let's consider the situation where I have maybe ABC graphene, where in valley K, it looks like this, and in valley K prime, maybe I have one band here, and in valley K prime, there's some other band like this. And then there might be some other more bands down here. Okay, so I have the K valley and the K prime valley. This point here is, say, charge neutrality, nu is equal to 0. And let's say I put the chemical potential at a point at filling 1, so that it wants to fill either this band or this band, but not both. So let me be at filling 1. Now, the naive thing you might do is to valley polarize, so to put all the electrons into this band or all the electrons into this band. That will correspond to a projector that's going to point in 2 particular possible directions. But as we said, you could do something more fancy, which is instead of going into that or that, you can instead go into a superposition of the K and K prime bands. And now what I want to do is evaluate within this Hartree-Fock setup, does it prefer to valley polarize or does it prefer to be intervalley coherent? Okay, so henceforth, I did this here with an arbitrary number of bands called M and N. Now I'm just going to have 2 bands, which I'll call lambda, the plus band and the minus band. So all these matrices I've been talking about, lambda and so on, are now just 2 by 2 matrices in the space of valley. Now, this situation is a nice one to illustrate all this formalism because the form factor ends up being somewhat simple. When we calculate lambda KQ, this is a 2 by 2 matrix. When we focus on small q, there's not enough momentum to lead to a matrix element between the 2 valleys. So as a result, whatever the form factor is actually going to be diagonal. So I can write it as some lambda plus KQ and lambda minus KQ. So diagonal is really nice because, when we were talking about the unitaries, I had to exponentiate the Berry connection. Now everything's going to be a diagonal matrix, so the exponentiation is going to be easy. Let me make one further approximation, which is exactly the approximation I made. I'm going to assume that the quantum metric is proportional to the identity. And what that means is I can assume that lambda plus or minus of KQ is equal to an amplitude which is independent of plus or minus, and then the phase, which I'll write as e to the I by q of k plus tau z, or basically plus or minus I tau. So I. Okay. So the fact that I'm assuming the form factor has the same magnitude for plus or minus is exactly this approximation that I assume that the quantum metric is proportional to the identity, that they have the same amplitude, and that they differ by this phase here, alpha q. Okay, so in other words, what it's saying is that the Berry connection, which is relevant here, A is basically equal to, if I write alpha q of k is approximately q dot A of k, then it's saying that the Berry connection AMN is just tau z times, this is all it's going to show up is the A of k. Okay, that was just a complicated way of saying that in this situation, our Berry connection is diagonal, so it's proportional to tau z. Okay, so the takeaway then is that we can immediately write down the form of the elastic energy, where our covariant derivative delta mu is Marshall mu plus okay. So I have a Berry connection, which is diagonal in tau z by the assumption of the diagonal form factor. Okay, so this now leads to a kind of cool result. Let me say, for the moment, let's assume that it is Intervalley coherent. And I'll probably have to cut this lecture short. So let's assume that the form of P is entirely Intervalley coherent. What that's basically saying is that the projector P is going to be equal to some cos of theta k tau x plus sine theta k tau y, if I assume the projector is pure Intervalley coherence. And then what I can do is ask, what is d mu p, d mu p, d mu p trace? And it's an interesting exercise to just take this and then substitute in for that particular diagonal Berry connection. And what we get is this is exactly twice So what's the takeaway here? Theta k is like the local in k space intervalley order parameter. And apparently under all these approximations, the elastic energy is like the gauge covariant derivative squared, right? Which is exactly the same Lagrangian as you get, for example, for a superconductor, right? So in the particular case where the metric g mu nu is diagonal, this thing just approximates nabla mu theta k, nabla theta k minus a squared, where a is the difference in the quantum geometry between the two bands which are intervalley coherent. So I'll probably have to end my lecture early, but let me just say why that's a kind of interesting phenomenon. So it says, suppose you have two bands whose quantum geometry differs by Berry connection A. A is the difference in their quantum, in their Berry connections. And then you assume it's intervalley coherent. Then it ends up having in K space the same Lagrangian as that of the Landau-Ginzburg theory of superconductivity in a magnetic field. This is like a fictitious magnetic field in K space. So in the particular case where the two bands have the same geometry, A would be 0. And the system is very happily able to minimize the elastic energy by just having a constant intervalley coherence across the Brillouin zone. On the other hand, if the curl of A is not 0, there's a magnetic field, it's like asking about the energy of a superconductor in a magnetic field. And we know when you have superconductivity in a magnetic field, it forces there to actually be vortices in the order parameter, and then it reduces, there's necessarily some elastic energy coming from that vorticity. So this then gives a very powerful way of thinking about intervalley coherence. Intervalley coherence is happy when you have the same Berry connection in the two bands which are hybridizing, and there's a penalty whenever there's a difference in the Berry curvature. Okay, but why did I then say that intervalley coherence is the theory of everything? Because often what happens is if you have the k and the k prime valley, because they're related by time reversal, by definition, they have opposite Berry curvature in each of them. So you would tend to then have that A is not equal to 0. I assume I'm over at this point, right? Yeah, so I'll just say the reason you end up getting intervalley coherence is then actually from the dispersion. So in this expression here, I assumed only intervalley coherence, i.e. that P was purely in the xy plane. But really more generally, I could also have valley polarization by writing this as sine phi plus cos phi tau z. Now, when the system points in the tau z direction, there is no A for that part of it because the Berry connection is diagonal. Okay. So what the system then will prefer to do is rather than being intervalley coherent, when you have the A, it actually prefers to point in the tau z direction and just be constant in tau z. So generally, it says that you actually don't want intervalley coherence. You want valley polarization in order to minimize this Fock term. The reason you do end up getting intervalley coherence, and I guess I can post my lecture notes to finish it, actually comes from the dispersion. So if you have a difference in the energy between K and K prime, the other part of the Hartree-Fock energy is the single particle dispersion. In the region where valley K is low energy, it wants to valley polarize this way. In the region where K prime is low energy, it wants to polarize this way. And so the easiest way to balance the two things, that you want a direction in this space which is able to cant in the z direction in order to follow the kinetic energy, but also minimize the elastic energy, is actually to be in the xy plane and then cant, rather than to polarize purely along z, which can't benefit from the potential. So that was clearly too quickly to explain, but for people who want to know afterwards, I'd happy to go to the back floor and give the rest of the argument for why the dispersion leads to intervalley coherence. But hopefully it was at least useful. I think this is beautiful, this idea of the nonlinear sigma model looking like a kind of elastic energy in K space. And I think it's a powerful way of thinking about Hartree-Fock.
So due to the time limits, we can only take one question here, and probably the additional question can be discussed at the speaker later. Is there any questions?
Yeah, thanks for the nice talk. If you write up the self-energy up to some approximation, do you know what it looks like in terms of these projectors, or like a quantum metric? Does it show up?
Self-energy meaning like within Hartree-Fock, what is the Hartree-Fock Hamiltonian? Yeah, sort of kind of by yeah, I mean, you can work it out. It's kind of by analogy to superconductivity, the difference between what is the expectation value for P and what is the pair potential. I mean, what you do is the Hartree-Fock Hamiltonian comes from taking this functional and then taking one derivative with respect to P. So you know it basically kind of looks like d mu d nu P, roughly speaking. Yeah.
So that's then Professor Zaletel